Imagine a massive research hospital, right? It's completely brought to its absolute knees.
For total operational paralysis.
Exactly.
Yeah.
I mean, doctors can't access digital charts. MRI machines are, failing to push imaging data to the servers. Even the pharmacy can't verify a simple prescription.
It's a nightmare scenario.
And the crazy part here is this catastrophic failure, it wasn't caused by, some sophisticated state-sponsored cyber attack or a ransomware cartel wanting Bitcoin.
Right. No hackers involved.
None at all. It happened because of a single looping error on the network floor that just went completely undetected. It triggered what we call a broadcast storm.
A massive cascading feedback loop of just raw data.
Yeah, and it completely overwhelmed the hospital's central processing power in seconds. And it took them days to manually trace physical cables and stop the bleeding.
Which is just wild when you think about it.
It really is. A severed fiber cable or, rogue broadcast shouldn't end your business. And today, we're making sure it doesn't. So, if you want to keep your competitive edge and actually keep your network alive in this hyper-connected marketplace, definitely hit subscribe right now. And please check the description for the architecture diagrams we were looking at today. Let's dive right into layer 2.
That hospital story, it's just a phenomenal case study in vulnerability.
It really puts things in perspective.
It does. As industry analysts, we see companies focus so heavily on the flashy software, right?
Yeah.
The cloud apps, the shiny user interfaces.
Because that's what the users actually see.
Exactly. But none of that matters if the foundational highway system of your network is just designed poorly.
Yeah, it all falls apart.
A single point of failure at the data link level can take down a billion-dollar enterprise before the IT security team even realizes, hey, we aren't actually under a malicious attack.
Which brings us perfectly to the current installment of our journey. So we are officially on Chapter 7 out of our 15-chapter arc in this Telecommunications for Managers series.
Making good progress.
Yeah, we are. Just to set the stage for you, in Chapter 6, we covered the session, presentation, and application layers.
Right, the upper layers.
Yep, we explored how application architectures dictate network traffic patterns and how those upper layer ports and sockets govern user-facing applications. Basically, we established how the software talks.
But software needs a physical reality to actually travel through.
Exactly. So today's focus is Chapter 7, Layer 2 Networking. We are bridging that gap between raw physical media and high-level routing.
We're unpacking the true unsung hero of the local area network.
So Layer 2, the data link layer, this is where the digital world genuinely meets the physical world, right?
It is. It dictates how data is formatted for transmission and, crucially, how access to that physical media is controlled.
Okay.
And there is a massive strategic point here that, honestly, many executives just overlook when budgeting for infrastructure.
What's that?
A localized network can operate completely on Layer 2 without ever needing an internet connection.
Wait, really? I want to make sure I'm wrapping my head around the scale of that.
Sure.
You're saying, an entire corporate campus, thousands of workstations, localized domain controllers, massive storage arrays, all of that could theoretically function at full capacity internally.
Oh, absolutely.
Without a single router connecting them to the outside world.
Purely internal endpoint connectivity and network segmentation, all of that is handled entirely by Layer 2 logic.
That's fascinating.
Yeah, it relies on Layer 1, the physical copper, the fiber or radio waves to move the actual electrical or optical signals, but the local intelligence, that is all Layer 2.
Okay, so when does routing actually come into play then?
The exact moment a message needs to cross a boundary to a different network, like, say, hitting a cloud server in AWS. That is when routing and the upper OS layers kick in.
Right, okay. But before we get into the really complex logic of Layer 2, I do want to touch on that physical foundation you mentioned.
The copper wires and fiber strands.
Yeah. When an enterprise is expanding, they're evaluating new physical media based on, availability, affordability, installability, and usability.
The core metrics.
Right. But usability seems highly susceptible to the actual physical environment.
Oh, it is entirely dictated by the environment. Let me give you a common corporate expansion scenario that we see in the market.
Yeah, let's hear it.
So a company is leasing a new floor in a commercial high-rise, right? And the contractors suggest running unshielded, twisted pair cabling, just standard UTP copper, straight up through the elevator shaft.
Oh, I see where this is going.
Right, because it provides this highly convenient, straight vertical path between, say, the server room on floor 4 and the new switch closet on floor 5.
On paper, that probably saves thousands of dollars in drilling new conduit.
Exactly, until the network goes live.
Right.
The massive electric motors that drive commercial elevators, they generate severe electromagnetic interference, or EMI.
Huh.
When those motors engage, they create this rapidly expanding and collapsing magnetic field. And because those network cables are unshielded copper.
Wait, so the magnetic field from the elevator motor is literally generating electricity inside the network cable.
Yes, exactly. It actually induces a rogue electrical voltage across the wire, scrambling the actual data signals.
Oh, wow. That's a disaster.
Total disaster. The network interface cards on either end read those induced voltage spikes as corrupted data.
So you just get massive frame drops.
That's the frame drops, constant retransmissions, and just terrible throughput. The network becomes functionally unusable every single time someone calls the elevator.
So usability really does require a deep understanding of environmental interference.
100%. The physical environment dictates the layer 1 physical media, which in turn supports the layer 2 logic.
Okay, so the physical media just sits there, allowing raw electrical movement.
Yeah, it's just the pipe. Layer 2 is what gives that movement structure, boundaries and identity.
And it does that by examining highly specific information packaged into a protocol data unit, right? A PDU.
Exactly. In modern Ethernet, which is governed by the IE 802.3 standards, this PDU is encapsulated by a data link header and trailer.
Now, we hear about AMC addresses constantly when dealing with endpoint hardware. That's media access control.
Right, the physical address.
The 48-bit address hard-coded into the network interface controller, the NIC. But how does a network manager actually leverage that beyond just, basic connectivity?
Well, it actually becomes a critical tool for IT asset management and edge security.
How so?
So a MAC address is typically displayed as 12 hexadecimal digits, right? The first 24 bits make up what's called the organizationally unique identifier, the OUI.
Okay.
The IE assigns these specific blocks to manufacturers. So Cisco has specific OUIs, Dell has theirs, Apple has theirs.
Wait, so if the OUI identifies the manufacturer, then a network manager monitoring traffic isn't just seeing random alphanumeric strings.
Exactly.
They're actually seeing the exact hardware profile of every device connected to the switch ports.
That is the immense management benefit right there.
Wow, okay.
Let's say your policy dictates that only corporate-issued Dell workstations are allowed on the internal wired network.
Pretty standard policy.
Right. And then suddenly, your monitoring tools flag an OUI registered to a consumer-grade Netgear wireless router broadcasting on a conference room port.
You instantly know someone plugged in an unauthorized rogue access point.
Precisely. It provides immense visibility into the physical hardware layer without needing, complex software agents installed on the devices.
That makes perfect sense for visibility. But there's another field in that layer I want to challenge you on, which is the maximum transmission unit, the MTU.
Ah, the MTU.
Yeah, the standard Ethernet MTU is 1,500 bytes. Why should a business leader care about the byte size of a network frame? I mean, that sounds strictly like a network engineer's problem.
Well, it becomes a business problem when it impacts throughput and user productivity.
Okay, fair point.
The MTU represents the maximum payload size, the actual usable data that can fit into a single Ethernet frame after you account for the layer 2 header and the frame check sequence trailer.
Okay, so if a radiology department is trying to pull a massive, say, 4 gigabyte MRI scan across the local network, and the MTU is only 1,500 bytes.
That 4 gigabyte file has to be chopped into millions of individual 1,500 byte payloads.
Oh, man.
And every single one of those frames requires its own header, its own MBA address processing by the switch ASICs, and its own error checking.
That sounds incredibly inefficient.
It creates a massive amount of computational overhead. If your business relies on transferring immense contiguous data sets like raw video rendering, medical imaging, or big data analytics, a standard 1,500 byte MTU is brutal.
It forces your expensive high-speed network hardware to work incredibly hard just processing headers instead of, actually moving data.
Exactly. It's like trying to move 1 million tons of freight across the country using a fleet of compact sedans. The highways get clogged not by the freight, but by all the individual cars navigating the road.
That is a great analogy. So how do we fix that?
This is why enterprise networks dealing with heavy storage arrays often implement what we call jumbo frames, increasing the MTU to 9,000 bytes.
Oh, wow. That's a huge jump.
It is. It drastically reduces the overhead and allows the switches to process larger chunks of data simultaneously.
There's a catch, though, right?
Always. This requires the entire physical path, every single switch, every NIC, every cable, to support that larger frame size, or the frames just get dropped.
Aligning the physical reality with the logical ambition.
Very well put.
So let's look at how that physical reality actually handles traffic flow. We know modern networks use switches, but to understand why they are so vital, we really have to look at the legacy hardware they replaced, right?
Yeah, the hub.
And this concept of CS mass CD, carrier sense, multiple access with collision detection.
Hubs created what we call a flat network, which is essentially a single massive collision domain.
So break that down for us.
A hub is just a multi-port repeater. It has zero intelligence. If it receives an electrical signal on port 1, it simply amplifies that voltage and blasts it out every other port.
Just screaming into the void. So how does a computer actually know a collision happened? We always hear they listen to the wire, but what is the actual physical mechanism there?
It comes down to electrical physics. A network interface card transmits data by sending specific voltage levels across the copper wire.
Okay.
And when it is transmitting, it is also actively measuring the voltage on that exact same wire.
So it's sending and listening simultaneously.
Yes. And if two computers try to send a frame at the exact same millisecond, those two electrical signals physically crash into each other on the shared wire.
And when two electrical signals combine, the amplitude spikes.
Exactly. The voltage literally doubles.
Wow.
The transmitting NICs immediately detect that overvoltage spike. They instantly know a collision occurred.
So what do they do then?
They immediately stop transmitting their data, send out a brief jam signal to ensure every other device on the network knows the wire is compromised, and then they execute a random back-off timer before trying to transmit again.
So mathematically speaking, the more nodes you add to a single hub, the more devices sharing that physical copper space, the higher the probability of those voltage spikes occurring.
The performance degrades exponentially. More collisions mean more retransmissions.
And more retransmissions mean the network eventually just grinds to a complete halt under its own weight.
Exactly. Which brings us to the MAC layer bridge, better known as the modern network switch.
Right, so upgrading to a switch separates a LAN into multiple distinct collision domains. How does it eliminate that shared electrical space?
Because every single port on a modern switch is its own isolated collision domain.
Okay, how does that work internal?
The switch uses application-specific integrated circuits, ASICs, and dedicated memory to actively learn the network topology. When a device sends a frame, the switch reads the source MSE address and records it in a MSE address table, associating that hardware address with the specific physical port it arrived on.
So it's building a map of who lives where.
Precisely. And because it has that map, it can make intelligent forwarding decisions.
Oh, okay.
When a new frame arrives, the switch examines the destination MSC address, instantly checks its table, and forwards the frame only out the specific port where the destination device resides.
The electrical signal never even touches the other ports.
Exactly.
But what if two devices try to talk to the same server port at the exact same time?
The switch has internal memory buffers. It receives both frames, queues them up in its memory, and just forwards them to the server port one after the other.
So no electrical collision, no voltage spike, no retransmissions.
Problem solved.
Switches solve the physical collision problem perfectly. But there is a logical issue that switches do not solve out of the box, right? I mean, a collision domain is physical, but a broadcast domain is logical.
This is where we return to that hospital scenario from the beginning of the deep dive.
Right, the broadcast storm.
Sometimes a device legitimately needs to query the entire network. For example, a workstation needs to find the DHCP server to get an IP address.
Sure.
It doesn't know where the server is, so it sends an Ethernet frame with an all-broadcast destination MAC address formatted as 12 Fs in hexadecimal.
The universal shout to everyone on the network.
Exactly. And when a switch receives a frame with an all-F destination address, it is strictly programmed to flood that frame out of every single active port except the one it received it on.
It has to, by design.
Right. So if you have 5,000 devices connected across a massive hierarchy of campus switches, and one device sends a broadcast,
All 5,000 devices receive it.
and they all have to process it, they all exist in the same broadcast domain.
Wait, so if someone plugs a network cable from a wall port directly back into another wall port on the same switch, they've just created a physical loop.
And that is exactly how broadcast storms are born. A device sends a single broadcast frame. Switch A floods it to switch B. Switch B floods it right back to switch A over that looped cable.
And switch A receives it again and, following its programming, floods it again.
Yes. And remember, these frames are traveling near the speed of light.
Right.
Within milliseconds, that single broadcast frame has been duplicated tens of thousands of times. The switch processors hit 100% utilization just trying to forward this infinite loop of garbage data.
So legitimate traffic literally cannot pass. The network just completely melts down.
Which makes massive, flat broadcast domains an existential threat to an enterprise.
So how do we fix that? How do we take a 5,000 node network and logically chop it up to contain these storms without buying thousands of individual, physically isolated switches?
We use virtual LANs, or VLANs. This is really the cornerstone of modern layer 2 enterprise architecture.
Okay, let's apply this to a specific business scenario.
Sure.
Let's say we have a media production company with 200 staff members. 150 are general administrative users, email, web browsing, basic SaaS applications.
Typical light traffic.
Right. But 50 of them are high-end VFX artists rendering massive 3D environments directly to a centralized network storage array.
Oh, those 50 artists are going to absolutely saturate the switchback planes.
Right. And the admin users will experience massive latency just trying to load a basic intranet page because the switch buffers are constantly full of 3D rendering data.
Exactly. Now, the knee-jerk executive reaction might be to authorize a massive capital expenditure for faster core switches.
Oh, for sure. Just buy more bandwidth.
But throwing hardware at a logical topology problem is wildly inefficient. The elegant solution is implementing VLANs.
Okay, how does that work here?
A VLAN allows you to logically segregate network traffic and isolate it to its own collection of ports, completely independent of their physical location.
So you assign the 50 VFX artists to, say, VLAN 20, and the 150 admin users to VLAN 10.
Exactly. Even if an artist and an admin are sitting at adjacent desks, plugged into the exact same physical 48-port switch in the wiring closet.
Logically, they are on entirely different networks.
Precisely. If a device in VLAN 20 sends a broadcast frame, the switch will only flood it out to the other 49 ports assigned to VLAN 20.
So the switch creates an impermeable logical wall between the VLANs.
Yes. By isolating the heavy, broadcast-rich traffic of the rendering team, you instantly clear the congestion for the administrative staff.
You optimize the entire infrastructure without spending a dime on new hardware.
It's brilliant.
But how does this scale across multiple switches? Like, if our VFX artists are spread across 3 different floors with 3 different switches, they all need to be on VLAN 20.
Right.
Do we have to run a separate physical cable between the floors for every single VLAN?
Oh, that would be an unmanageable nightmare.
Yeah, it sounds like it.
If you had 20 different departmental VLANs, you would need 20 separate trunk cables connecting every switch in the building.
Which defeats the purpose.
Exactly. Instead, we use VLAN tagging, which is defined by the IE 802.1Q standard.
Okay, break down the mechanics of 802.1Q for us. How does a single physical cable carry isolated traffic for dozens of different networks simultaneously?
We configure the connection between the switches as a trunk link.
Okay.
When switch A needs to send a frame from VLAN 20 to switch B, it actually modifies the Ethernet frame. It cracks open the layer 2 header and inserts a tiny 4-byte tag into the frame before transmitting it across the trunk.
Wait, let me connect this back to what we discussed earlier about MTUs.
Go for it.
If a standard Ethernet frame has an MTU payload of 1,500 bytes, plus the standard 18 bytes of header and trailer, it's 1,518 bytes total.
Correct.
If the switch suddenly jams an extra 4-byte 802.1Q tag into the header, the frame is now 1,522 bytes.
You nailed it. And that is exactly where legacy hardware failed.
Really?
Early switches had physical ASICs hard-coded to drop any frame larger than 1,518 bytes because they assumed it was a malformed transmission. They actually called them baby giant frames.
Oh, wow.
Modern switches are specifically engineered to accommodate that 1,522-byte tagged frame.
That is fascinating. The logic actually forced a change in the physical hardware requirement.
It did.
So the receiving switch gets this slightly larger tagged frame. What happens next?
It reads that 4-byte tag, identifies that it belongs to VLAN 20, strips the tag completely off, and then forwards the normal untagged frame exclusively to the local ports assigned to VLAN 20.
So the end-user workstation never even knows the tag existed.
Exactly. It seamlessly extends the isolated broadcast domains across the entire campus.
And there's a critical management feature hidden inside that 4-byte tag, isn't there? The priority code point, or PCP.
Ah, yes. The PCP is a 3-bit field within the 802.1Q tag that allows network administrators to dictate class of service, or COS.
Okay, why does that matter to leadership?
It gives executives the power to prioritize certain types of data during times of heavy network congestion.
Give me a scenario where class and service prevents an operational failure.
Voice over IP, VIP, is the classic example here.
Right.
Voice traffic is UDP-based and incredibly sensitive to latency and jitter. If a voice packet is delayed in a switch buffer for even 50 milliseconds, the call drops audio, sounds robotic, and just ruins client communications.
And nobody wants that.
Right. An email, on the other hand, can be delayed for a full second, and the user will never even notice.
So using the PCP field, the network team configures the switches to look at the tags.
Exactly. They mandate a policy. Any frame originating from the VoIP VLAN gets tagged with a high-priority code point.
Okay, so it cuts in line.
Pretty much. When a core switch experiences a sudden surge of traffic and its buffers fill up, it doesn't just process frames on a first-come, first-served basis anymore.
It reads the PCP tags, pulls the voice traffic out of the queue, and pushes it through first.
It ensures the strategic priorities of the business actually dictate the technical behavior of the hardware.
I love that. So we have built these beautiful, highly optimized, isolated VLANs.
Very optimized.
But if the single physical trunk link connecting the floors gets accidentally severed by a maintenance worker, the entire logical structure dies.
It does.
How do we build physical backup cables for redundancy without instantly causing the broadcast loops we talked about earlier?
This introduces a really vital executive distinction. Redundancy versus resiliency.
Okay, define those for us.
Redundancy is the physical duplication of assets. Buying 2 core switches, running 2 fiber optic backbone cables between buildings. It is fundamentally a capital expense.
Just buying more stuff.
Right. Resiliency, however, is the logical capability of the network to dynamically utilize that redundant hardware to maintain availability during a failure.
And the catch-22 of Layer 2 is that redundant links, physically connected at the same time, create infinite loops.
Exactly. Which is why the spanning tree protocol, STP, was invented.
Ah, STP.
STP uses this brilliant distributed algorithm to map the physical topology, identify every possible loop, and strategically place redundant links into a logical blocking state. They act as hot standbys.
I want to dig deep into this because it honestly sounds like magic.
It kind of is.
You have a dozen switches plugged into each other. There is no central server managing them. How do a bunch of independent metal boxes agree on the topology without creating a loop, just trying to communicate with each other?
They use specialized multicast frames called Bridge Protocol Data Units, or BPDUs.
BPDUs. Okay.
The instant you power on the switches, before they forward a single piece of user data, they start transmitting BPDUs out of every port. Step 1 is the election of the root bridge, the central reference point for the entire network.
How do they vote? Do they campaign?
Kind of. Every BPDU contains a bridge ID, which is a combination of a configurable priority value and the switch's hard-coded MC address.
Okay.
The switch with the lowest bridge ID wins the election and becomes the root bridge.
Wait, if the priority value is configurable, what happens if the network admins just plug everything in out of the box and don't configure anything?
By default, every single switch leaves the factory with a priority value of 32768.
So they all tie.
Yep. So if there is a tie on the priority, the tiebreaker is the lowest ME address.
But MC addresses are assigned sequentially by the manufacturer during production.
Exactly.
So the lowest ME address would belong to the oldest piece of hardware.
Yes. If a manager doesn't properly configure the STP priority, the brand new $1 million 40 gigabit core switch might lose the election to a dusty 10-year-old 100 megabit switch sitting in a janitor's closet just because it was manufactured first.
Oh my God.
And that old switch becomes the root bridge, and the entire network dynamically recalculates its topology to force all traffic through that ancient bottleneck.
That is a terrifying operational blind spot.
It happens more than you'd think.
So, assuming it's configured correctly, we have our root bridge. What happens next?
Every other switch in the network must calculate its root port. This is the single physical port on the switch that offers the best, most efficient path back to the root bridge.
How is best determined? Is it just the fewest number of hops?
Actually, no, it is based on path cost, which is inversely proportional to the link bandwidth.
Okay, so speed matters.
Right. A 10 gigabit fiber link has a much lower path cost than a 1 gigabit copper link. The switch adds up the cumulative cost of the links to the root bridge. The port with the lowest total root path cost becomes the root port.
Okay, so once the root ports are established, how does it actually stop the loops?
By electing designated ports for every network segment, and then taking the final critical step, any port that is not a root port and not a designated port, is forced into a blocking state.
It just stops sending and receiving user data entirely.
Completely blocked.
So I'm trying to picture this. It's almost like a GPS navigation system mapping out a road trip, right?
Sure.
It sees all the possible highways. But to prevent you from driving in an endless circle, the GPS logically places roadblocks on the backup routes.
That's a highly accurate way to visualize it.
The physical asphalt is still there, but traffic is forbidden from driving down it.
Exactly. The links are physically connected, drawing power, but logically severed.
So what happens if a backhoe digs up the primary fiber line? If the main highway washes out?
The switches stop receiving BPDUs on that active port. They instantly detect the failure, recalculate the algorithm, remove the logical roadblock on the backup port, and transition it to a forwarding state.
That's brilliant. But this creates a serious friction point with the finance department, doesn't it?
Oh, absolutely.
A CFO looks at an IT audit and sees a $100,000 secondary fiber optic trenching project, and the network team says, yeah, STP has that link in a blocked state. It's transmitting zero data.
It's a tough conversation.
How does an IT leader justify the ROI on a completely dormant asset?
You don't justify it as an operational asset, you justify it as an insurance policy.
Okay, I like that.
You pivot the conversation to risk management and fault tolerance. The metric isn't utilization, it's the cost of downtime.
Right.
If a primary link failure disconnects the logistics warehouse from the central database, and the business bleeds $250,000 an hour in lost shipping revenue.
That $100,000 dormant backup link pays for itself within the first 30 minutes of a severed cable.
Exactly. It's all about mitigating risk.
Now, as brilliant as the original spanning tree protocol is, there was a massive limitation when dealing with modern applications, right? The convergence time.
Yeah. Legacy STP, which was developed in the 1980s, relied heavily on passive timers.
Okay.
If a link failed, it took 20 seconds for the max age timer to expire just to confirm the BPDU is missing.
That's an eternity in networking.
And then another 30 seconds of listening and learning before the blocked port transitioned to forwarding.
Right. A 50-second network outage in the 1980s was probably nothing.
Nobody noticed.
But a 50-second outage today drops every single active VoIP call, severs VPN tunnels, and corrupts active database transactions.
Which is why the industry evolved to Rapid Spanning Tree Protocol, or RSTP.
RSTP. How does it fix the timer issue?
RSTP fundamentally alters the convergence mechanics. It abandons passive timers in favor of active negotiation handshakes between the switches.
Oh, so they talk to each other directly?
Yes. When a topology changes, RSTP switches actively query each other, rapidly flushing their MOC address tables and synchronizing their forwarding states.
How fast is the recovery?
Standard topology changes converge in under 6 seconds.
That's a huge improvement.
And it gets better. If a switch detects a direct physical link failure on a point-to-point connection, it can unblock an alternate port in milliseconds.
Wow.
The failover is so fast that active phone calls might not even drop.
That's incredible. And there's one more variation we have to cover here.
Huh.
Multiple Spanning Tree Protocol, MSTP, defined by IE 802.1s.
Yes, MSTP.
How does this solve the CFO's complaint about dormant links? Because they still want to see assets being used.
Right. So with standard STP or RSTP, you have one spanning tree for the entire physical network. If a link is blocked, it is blocked for every single VLAN.
Completely dark.
Exactly. MSTP, however, allows network architects to map multiple spanning tree instances to specific groups of VLANs.
Wait, so you could configure the algorithm so that the physical fiber link on the left is actively forwarding traffic for, say, VLANs 10 through 50,
Yep.
but blocking VLANs 51 through 100 to prevent loops?
Exactly. And the physical fiber link on the right does the exact opposite.
Oh, that's clever.
It blocks VLANs 10 through 50, but actively forwards 51 through 100.
So both physical links are actively utilized, balancing the load across the core infrastructure.
While still maintaining complete loop-free redundancy for every individual VLAN, it maximizes the ROI on your physical cabling, which keeps the CFO happy.
That perfectly transitions into our next major strategy for maximizing throughput. We've solved loops, we've optimized redundancy.
Right.
But what if we simply need more raw bandwidth between two buildings, and a single cable just isn't enough? This is where we leverage IETH A2.3 add, link aggregation.
Also known as port trunking, NIC teaming, or ether channel, depending on the vendor.
Okay, what makes it so useful?
Link aggregation is an incredibly elegant technology that allows network administrators to bundle several physical Ethernet links in parallel, combining them into a single massive logical interface.
Walk us through the actual mechanics. How does the switch actually split the data across multiple cables without scrambling the order of the frames?
That's the complex part. If you bundle four 1 gigabit cables together, you don't actually get a single contiguous 4 gigabit pipe. You get four separate lanes.
Okay, so it's a multi-lane highway.
Right. And if a switch just round-robin the frames, sending frame 1 down cable A, frame 2 down cable B, and so on, the frames would arrive at slightly different microsecond intervals.
And out-of-order frames at layer 2 cause massive CPU overhead as the receiving device tries to, reassemble the data stream.
Exactly. So link aggregation uses the Link Aggregation Control Protocol, LACP, alongside complex hashing algorithms.
Hashing, okay.
When a switch needs to send data across the bundle, it runs a mathematical hash against the source and destination IP addresses or MAC addresses of that specific session.
So a specific file transfer between a workstation and a server will consistently hash to the exact same value.
Yes. And the switch uses that hash value to pin that entire data session to one specific physical cable within the bundle,
So the frames for that session always travel down the same wire.
ensuring they arrive perfectly in order. Meanwhile, a different user transferring a file to a different server generates a different hash, and their traffic is pinned to a different physical cable in the bundle.
So it's essentially load balancing across the physical links based on the session flows.
Exactly.
What is the strategic takeaway for an IT director here?
Link aggregation allows an enterprise to rapidly and cost-effectively scale bandwidth on demand without ripping and replacing expensive legacy chassis switches to buy faster single-port optics.
That's a huge cost savings.
It really is. If a 10 gigabit uplink is congested, you don't need to buy a $20,000 40 gigabit interface card. You just run two more cheap 10 gigabit fiber strands, bundle them with LACP, and you instantly have a 30 gigabit logical backbone.
And it inherently provides fault tolerance too, right?
Sure.
If one of those three fiber strands is damaged, the logical link doesn't go down.
Right. LACP detects the physical loss, dynamically removes the failed cable from the hashing algorithm, and seamlessly redistributes the traffic across the remaining active links.
So the total bandwidth drops, but the connection remains entirely stable.
Precisely.
That's fantastic. Now let's pivot to a capability of modern Layer 2 edge switches that completely blurs the line between data infrastructure and facility management.
Power over Ethernet, PoE.
Yes, PoE. How has this changed the game?
Well, PoE fundamentally changed how we deploy edge devices. Modern switches don't just route data anymore. They inject low-voltage DC power directly down the exact same standard Cat5e or Cat6 copper cables that carry the Ethernet frames.
Eliminating the need to hire expensive electrical contractors to install 120-volt AC outlets in the drop ceilings every time you want to, say, mount a Wi-Fi access point.
The cost savings on electrical contracting often pay for the upgraded PoE switches outright.
I believe it.
And it's not just basic wireless access points anymore. With the evolution of PoE Plus and PoE++ standards, switches are delivering up to 60 or even 90 watts of power per port.
That's a lot of power for a data cable.
It is. They are powering massive pan-tilt zoom security cameras, point-of-sale terminals, biometric door locks, and even LED smart lighting systems for entire office floors.
You actually mentioned an incredibly specific use case earlier regarding facility synchronization. Digital wall clocks.
Yes. In environments like a hospital trauma ward, a stock trading floor, or a university testing center, absolute time synchronization is legally and operationally critical.
You can't just rely on battery-operated analog clocks drifting over time.
Exactly. You deploy digital wall clocks powered entirely by PoE.
And the switch uses the network time protocol, NTP, over that exact same data connection.
Every single clock in a massive multi-building campus displays the exact same millisecond of time, continuously synced to a master atomic clock, all powered and managed by the Layer 2 switch infrastructure.
The network basically becomes the electrical grid for the smart building.
It really does.
So we have dissected the tools, VLANs, spanning tree, link aggregation, PoE.
The core tools.
To tie this all together, how do these concepts scale? How does the topology physically look depending on the size of the business?
We can categorize this into three distinct scales. First is the SOHO, the small office home office.
Like a local insurance agency or a remote branch.
Right. The Layer 2 design here is very minimal. A single piece of hardware, a router with an integrated firewall, and a built-in 4-port or 8-port switch is sufficient. The topology is entirely flat.
Because The scale just doesn't justify the complexity of VLAN segmentation.
Exactly.
But when that agency grows into, say, a 100-person regional headquarters, we enter the SMB space, the small and medium-sized business.
And at the SMB scale, a flat network becomes a massive security and performance liability.
So what's the solution there?
This is where organizations adopt a collapsed backbone topology.
Paint a picture of a collapsed backbone for us.
Picture a hub-and-spoke model. You invest in one highly capable, high-speed core switch, the collapsed backbone. Then all the individual edge switches located in different departments connect directly back to that single core switch.
Okay, I see.
This is where VLANs become mandatory for security. The edge switch in the HR department is physically separate, but logically, the payroll clerks are isolated on an encrypted VLAN that terminates at the core switch.
Ensuring the marketing interns can't accidentally browse to the payroll server.
Exactly. Security through segmentation.
And finally, the enterprise scale. We're talking a sprawling university campus or a multi-building corporate headquarters.
Right. A single collapsed backbone cannot support the physical distance or the massive port density of an enterprise. You move to a hierarchical campus backbone.
How is that structured?
Every single building has its own internal collapsed backbone, often with redundant core switches running rapid spanning tree. Then, those building-level core switches connect back to a massive, centralized data center via redundant, aggregated long-haul fiber optic trunks.
Now, at that sprawling enterprise scale, I have to ask about physical edge security.
It's a huge concern.
If a university has 10,000 active Ethernet ports in dorm rooms, library cubicles, and public lecture halls, what is actually stopping a malicious actor from plugging a laptop into a wall jack, running a simple script, and intentionally flooding the network with millions of BPDU frames or broadcast packets to cause a massive denial of service attack?
That is a highly sophisticated attack vector. When an attacker floods the network with superior BPDU frames, trying to force their rogue laptop to become the root bridge, it can completely hijack the spanning tree topology.
So how does the network manager defend against an attack targeting the foundational protocols?
Enterprise-grade Layer 2 switches utilize advanced port security features, specifically BPDU guards and switch floodguards.
Okay, how does a BPDU guard work?
A BPDU guard is configured on all edge ports facing end users. The logic is simple. A user workstation should never be transmitting spanning tree BPDUs.
Right, why would a laptop be doing that?
Exactly. So if the switch suddenly detects a BPDU frame arriving on a library cubicle port, it instantly assumes it is under attack or someone plugged in an unauthorized switch.
And how does it react?
The switch hardware immediately forces that specific physical port into an error-disable state.
It just shuts it down.
It completely shuts down the port's ability to transmit or receive data, instantly quarantining the threat at the very edge of the network before it can influence the core topology.
That's incredibly effective. What about the floodguards?
Similarly, floodguards monitor the baseline broadcast traffic of every port. If a port suddenly starts vomiting thousands of broadcast frames per second, the floodguard trips and drops the interface.
It is an automated, hardware-level immune response.
That's a perfect way to describe it.
And it perfectly encapsulates the entire theme of our discussion today.
Yeah.
Layer 2 is not just, dumb plumbing moving electricity from point A to point B.
Not at all.
It is an intelligent, highly configurable foundation that protects, optimizes, and powers the entire business enterprise.
By mastering these concepts, VLAN segmentation to isolate critical traffic, link aggregation to scale throughput dynamically, and RSTP to provide instant, loop-free failover executives transform their underlying infrastructure from a fragile liability into a resilient strategic asset.
Right.
A severed backbone cable or a rogue device shouldn't trigger a corporate disaster. It should merely generate an automated work ticket while the Layer 2 logic seamlessly reroutes the data without dropping a single active session.
That is the ultimate managerial takeaway. I want to sincerely thank you for joining us on this deep dive.
It's been a pleasure.
Now, looking ahead, we are seamlessly moving up the OSI model. I want to tease our upcoming chapter, Chapter 8, Layer 3 Networking. Now that we have optimized the local network and built these resilient campus backbones, how do we actually connect them to the rest of the world?
That is the complexity of scale. Layer 2 gets data across the room. Layer 3 gets it across the globe.
Which is a whole different ballgame.
Managers must stay tuned to solve the next massive piece of the infrastructure puzzle. How routers actually interconnect disparate, physically distinct networks and calculate optimal wide area pathways using dynamic link state and distance vector protocols like OSPF and BGP.
We are going to explore the exact mechanisms that route traffic across the internet.
It's going to be a great discussion.
Before we go, I want to reiterate our early ask. Please subscribe and share this content if it brought you strategic value. Be sure to check the description for the vital resource links and network diagrams we referenced today.
Very important resources in there.
Also, explore the channel for our other corporate IT modules designed for continuous executive education. I highly recommend diving into the Digital Forensics series, as well as our Network and Systems Security series. Both are essential listening for modern IT leaders.
Think critically about the architecture supporting your own organization right now. If your physical cables were suddenly cut today, does your Layer 2 logic genuinely have the resiliency to keep your business alive tomorrow?
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.